All right, let's get right into it. Today, we are going on a journey into the hidden world of materials. We're going to start with the perfect atomic blueprints that make up everything. And then, we're going to discover how the flaws in those blueprints are what give materials their most incredible powers. So, have you ever really stopped to think about this? Why can you bend a paperclip, but a diamond, the hardest thing we know, would just shatter? Or how on earth does your phone battery, this solid little slab, somehow store and release energy over and over again? Well, the answers to all these questions aren't on the surface. Nope, they are hidden away at a scale that is just mind-bogglingly small in the invisible architecture of how atoms arrange themselves. And that is exactly what we're going to unpack. So before we can really appreciate the flaws, we have to understand the perfect plan. Let's start with the ideal, the perfectly ordered universe inside of a crystal. You see, every crystalline material, from a tiny grain of salt to a huge steel beam, has what we call a crystal structure. It's this endlessly repeating 3D pattern of atoms. The best way to picture it is like atomic wallpaper, or maybe like those perfect pyramids of oranges you see at the grocery store. This is the material's fundamental blueprint. Now here's the thing. Not all of these atomic blueprints are created equal. One of the biggest differences between them is just how tightly the atoms are packed together. And we have a way to measure this. It's called the atomic packing factor, or APF for short. And the difference is actually huge. Look at a simple cubic structure. It's only 52% full of atoms. That means it's almost half empty space. Body-centered cubic gets a bit better, up to 68%. But the real champion is face-centered cubic, which packs in at 74%. That is the most efficient way you can possibly pack spheres. And it's a huge reason why metals like copper and aluminum are so easy to bend. The atoms have these dense planes that can easily slide along. Okay, so that covers simple metals where all the atoms are the same. But what about the really complex stuff, like ceramics, where you have different atoms with positive and negative charges? For that, we need a whole new instruction manual. And that manual comes from the brilliant Linus Pauling. He came up with 5 rules that basically predict how these complex ionic crystals build themselves. For instance, the very first rule, the radius ratio, is just pure geometry. It's all about how many negative ions can physically squeeze around a positive one. And then you have rule 3, which says it's way more stable for these atomic shapes to just share corners instead of whole faces. Why? Well, it keeps the positively charged centers as far apart as possible. The whole thing is like a self-assembling puzzle, all guided by these really elegant rules. Let's just zero in on that first rule, because it is so important, the radius ratio. All it is the size of the positive ion divided by the size of the negative one. That's it. And yet this one simple number pretty much dictates the entire geometry and stability of the crystal. It's wild. Okay, so we've seen the perfect blueprint. We get the rules of order. But now comes the plot twist. It turns out that, in the world of materials, perfection is actually kind of useless. The real magic happens in the mistakes. I absolutely love this quote. A theoretically perfect crystal would be unbelievably strong. Yeah, but it would also be brittle and honestly pretty boring. It's the flaws, the imperfections, those little deviations from the perfect blueprint, that's what gives materials all their unique and most valuable properties. And these flaws aren't all the same. We can actually categorize them by their dimension. You've got your zero-dimensional or point defects, which is like a single atom just missing. That's called a vacancy. Then there are one-dimensional line defects called dislocations. You can go up to two-dimensional planar defects like the boundary between two different crystal regions. And finally, you get to three-dimensional volume defects like a tiny crack or a pore. And it's really important to know where these things come from. Some of them are just statistical flukes, random mistakes that happen when the crystal is growing. But others are actually structural. They're an ordered, totally necessary part of the material's architecture. A great example is when a whole bunch of dislocations line up to form the boundary between two slightly misaligned crystals. So, how do these tiny little flaws actually translate into properties that we can see and use in the real world? Well, this is where it gets crazy, because they can take what seems like a weakness and turn it into a superpower. Now, here's a key distinction you have to get. Some properties, like, say, the density of a material, they don't really care if there are a few defects scattered around. But other properties, we call them structure-sensitive properties, they are completely dominated by these flaws. And here is the most mind-blowing example of all: yield stress. That's the force it takes to permanently bend something. A perfect iron crystal would have a yield stress in the gigapascals. It would be insanely strong but brittle. But then you introduce some dislocations, those little 1D line defects, and the yield stress plummets by a factor of 1,000, down to megapascals. That huge drop is the entire reason metal bends. It's why you can shape a paperclip. The dislocations literally move and allow the atomic planes to slip past each other. So what about that battery question from the beginning? It is all about defects. Those empty atomic spots, the vacancies, they create little ion highways so lithium ions can just zoom through, which gives you fast charging. Dislocations help the material soak up the strain as ions move in and out, preventing cracks. And the impurity atoms we add on purpose, dopants, they fine-tune the whole thing for faster electron flow. We don't just tolerate these flaws, we engineer them in. Which brings us to the final and maybe most exciting piece of the puzzle. If these flaws are so useful, so powerful, how do we actually control them? How do we become the architects of these atomic imperfections? Well, the go-to method, the real workhorse, is something called solid-state synthesis. The idea is actually pretty simple. You take a bunch of different powders, you mix them all together, and you cook them. You heat them up until the atoms get enough energy to jump around and rearrange themselves into a totally new crystal structure, complete with all the beautiful flaws you want. And here's the basic recipe. First, you grind everything into superfine powders to get as much surface area as possible. Then you press all that powder into a tight little pellet so everything's touching. Then comes the critical step. You bake it or sinter it at really high temperatures to get those atoms moving. And after that, you cool it down, you check what you made, and more often than not, you do it all over again until you get it perfect. So just how hot do you have to go? Well, there's a fantastic rule of thumb for this called Taman's rule. It basically says that for atoms in a solid to really get moving and start reacting with each other, you have to heat them to at least 2/3 of their melting point. And you have to measure that in Kelvin. Any cooler than that, and you'll be waiting forever. So by mastering this whole process, choosing our ingredients, controlling the temperature, being patient, we gain control. We can finally design not just the perfect atomic blueprint, but we can also engineer the number, the type, and even the location of all the beautiful flaws that give a material its true power. And that's really the big takeaway here. Humanity has moved from an age of just finding materials in nature to an age of designing them. Literally atom by atom, flaw by flaw. We are learning to speak the language of crystals and command their imperfections. It just makes you wonder, what are we going to build next?